Hi, in previous part, we have seen detailed review of these amazing LoRa development boards, Wio-E5 Dev Kit and Wio-E5 Mini, manufactured by the Seed Studio. We have seen its unboxing, features, specifications, datasheets, AT commands configuration guide, and we have also seen demo of serial configuration of these boards via AT commands. In this part, we will see one DIY project using these boards. So, let's get started.
Hello all, welcome to Make 2 Explore channel. First of all, thank you to all our subscribers, viewers and supporters. In this video, we will see one interesting project based on these two LoRa development boards by Seed Studio. We have seen their detailed review in previous part. We will use them to design DIY project to test application of LoRa WSN, wireless sensor network, in landslide monitoring or detection systems. But before going into project design, let's know about landslide, a natural disaster. Let's see the theory and problem statement of project. So what does actually mean by landslide? A landslide, which is also called as landslip, is defined as the movement of massive rock, debris, or earth down a slope. You can see this in animation. There are several forms of mass wasting that may include a wide range of ground movements, such as rockfalls, deep-seated slope failures, mudflows, and debris flows. Landslides are a type of mass wasting which denotes any down-slope movement of soil and rock under direct influence of gravity. Here, gravity is the primary driving force for a landslide to occur, but there are other factors affecting slope stability that produce specific conditions that make a slope prone to failure. In many cases, the landslide is triggered by a specific event, such as a heavy rainfall, an earthquake, a slope cut to build a road, and many others. Although this is not always identifiable, landslide is a critical natural geological hazard that causes severe damage to property, infrastructure, and humans. Historical landslides occurred around the world, caused disasters, deaths of number of peoples, and destroyed homes, structures, and loss of plant lives. Hazards are mitigated mainly through precautionary means, for instance, by restricting or even removing populations from areas with a history of landslides, by restricting certain types of land use where slope stability is in question, and by installing early warning systems based on the monitoring of ground conditions, such as strain in rocks and soils, slope displacement, and groundwater levels. So there are several landslide monitoring techniques researched in last decades, but they are broadly categorized into three major classes: statistical methods and rating scheme, remote sensing, and ground-based systems. We are going to use our Wio-E5 LoRa modules in this ground-based system for improving its wireless connectivity. But before that, let's see about what are these techniques in detail. Statistical method and rating schemes are completely analytical methods, where numerical weights are assigned to each of the triggering parameters of the landslide. All the ratings are summed up to get an aggregated value used to determine a landslide's likelihood. The higher the value obtained, the higher would be the probability of landslide. This method can develop landslide hazard mappings to identify the potential landslide hazards in the area. It is simple, but it suffers from subjectivity, as experts' evaluation is based on analytical studies, and personal biases may interfere while assigning ratings to each parameter. Second category is remote sensing. In remote sensing, the sensors acquire data while deployed at remote locations. This method does not consider intrinsic parameters, which have a high degree of influence on landslides occurrence. Besides, these systems are not much helpful in prediction, but very significant in real-time monitoring. Techniques used in this category are SAR, LISA, and LIDAR. SAR means synthetic aperture radar, One of the main applications of synthetic aperture radar (SAR) interferometry is the monitoring of natural hazards, in particular of those phenomena producing ground displacements. SAR uses electromagnetic radiation for generating images of the hill slopes. The images must be clear and of high quality to get an accurate and reliable estimation of the landslide detection. LISA stands for Linear SAR, Linear Synthetic Aperture Radar. LISA is a ground-based system. LISA gets images of the area from the ground, minimizing the weathering effect in getting quality imagery. And next is the light detection and ranging. LiDAR is a terrestrial portable scanning technique. The slope area is scanned to obtain data that is then correlated to determine any deformation. This technology is suitable in environments where the deformation is determined only by the morphological data. For example, pit mining can be monitored using LiDAR applications. Global Positioning System (GPS). GPS is also used for locating the areas of active landslides. It is feasible for landslide detection. Another technique in this category is photogrammetric technique. The photogrammetric technique uses 3D specialized cameras for monitoring ground movement in the mining areas. Cameras are installed at a height to observe the terrain. In imagery-based monitoring systems, the images obtained may be blurred, affecting the landslide detection process. Deep learning-based algorithms helps to improve the quality of the images. Next important category of landslide detection techniques is ground-based systems. In ground-based techniques, the sensing devices directly contact the terrain, acquiring real-time data, means they are intrinsic, actual in contact with ground and terrain. Techniques covered in this category includes antennas. Antennas are placed at different locations on a terrain. The tilt in the position of the antenna suggests the displacement of the surface. This method is supported by using the analytical hierarchy process in GIS. It is useful only to detect mud sliding when it happens, ignoring most of the triggering factors. Next technique is OTDR, means optical time domain reflectometry, which is used for monitoring debris flow. It uses fiber optic sensors, reflectometer, that detect vibrations generated due to ground movements. Practically, the reflectometer bends when the ground experiences displacement. And another techniques are WSN-based methods, wireless sensor networks, used for monitoring and detection of land sliding. Since its inception, WSN-based monitoring systems for landslides receive significant attention. In WSN systems, different type of wireless networks can be used, like cellular GSM, Wi-Fi, Zigbee radio, or RF, etc. We are going to test LoRa wireless technology. For that, we are going to use Seed Studio's Wio-E5 series LoRa development boards. We are going to test how we can transmit and relay different sensors data collected in these different sensor nodes to the end node, which will be located at nearby town or city, where local authorities can monitor, analyze it with statistical method and rating schemes to predict or early detect any posed disaster in near future. We will see this in detail in coming slides. Recently, in year 2022, place named Joshimath in Uttarakhand state of India, landslide events are happening. ISRO, the Space Research Agency of India, used remote sensing technique and released some satellite images about the subsidence happening in following 6 months. So you can see the subsidence zone and its value, around -5 centimeters approximately. These are remote sensing findings, but actual ground reports are far more hazardous. You can see these pictures. Okay, therefore, we can say that, although satellite-based remote sensing results and findings are significant, but they also should be backed up by actual ground-based monitoring systems for more accurate results. Here, in such cases, the LoRa-based WSN can play an important role in wireless communication part. By monitoring descending velocity of mass in landslide or subsidence over period of time, and by using statistical analytical techniques of likelihood findings, we can predict or early detect the landslide events. Here in this table, there are different types of landslide events are categorized according to the descending velocity of mass or debris. So as per these stats, in point of view of safe evacuation of peoples living in landslide-prone areas, these 4 landslide events can be easily early detected, and loss of lives can be avoided. Extremely slow, very slow, slow, and moderate movements landslides can be early detected before they enter into rapid and extremely rapid modes. So this was all about problem statement. Now let's see where the actual implementation of our DIY project stands in these kind of systems. Please note that project which we are going to design is not about high quality or innovative detection or sensing. We are going to cover only communication part. Means how LoRa WSN can be helpful in reliably, effectively and efficiently conveying monitored data to the distant concerned authorities. Let's see the scenarios of project's application. We will consider 3 main cases. First, landslides occurring at remote villages near mountains, cities or towns near mountains, and roads or highways passing through hilly regions. If we consider this city's case, then use of LoRa WSN or LoRa WAN will be unnecessary here because other more faster and reliable wired or wireless communication services like Ethernet, GSM 5G, Wi-Fi will be available near this town. But for other 2 scenarios, there may be lack or unavailability of cellular or Wi-Fi networks. In such areas, to monitor data of the landslide events, LoRa wireless sensor networks can play a very important role. If these sites comes in range of 5 to 10 kilometers from well-connected city, then P2P LoRa or LoRa WAN can be used. Moreover, P2P means point-to-point LoRa network will be more affordable than that of LoRa WAN. Since our area has very poor connectivity of LoRa WAN gateways, we will consider this 3rd scenario for implementation of our project as more sophisticated. Let's see this scenario in detail. Most of the time, roads passing through mountains lacks wireless connectivity. Landslides occurring in such areas may cause accidents and closure of the roads. If any landslide monitoring system deployed in such areas, it is very difficult to send its data to concerned authorities if cellular networks have no coverage. That's why we are proposing solution with LoRa WSN, since LoRa can easily cover distance up to 5 to 10 kilometers. Therefore, in short, this project is not about implementation of any new landslide monitoring or detection system, but to study of how we can use or utilize the LoRa technology as WSN, wireless sensor network, in existing well-equipped landslide monitoring systems. Then why use of LoRa technology? A challenge in landslide monitoring through other WSN is that each sensed data item might be critical, whereas the underlying wireless communication is often unreliable. In case of landslides, the terrains have irregular shapes, providing harsh conditions for wireless communication. Therefore, sometimes these areas lacks connectivity. Though coverage of cellular technology is vast, but sometimes in these mountain regions, or roads in these areas, often comes in shadow regions of connectivity. Here use of LoRa can be better option to fill the gap of connectivity. Now let's see how Wio-E5 LoRa modules will be used in this project. Suppose there is landslide monitoring system, which incorporated different LoRa wireless sensor nodes. Suppose this system has been deployed at landslide-prone area and hilly road, where Wi-Fi and cellular networks are unavailable. This system is connected to nearby cities and highway patrol authorities via LoRa. For that, we will use Wio-E5 Dev Kit as sensor node. In actual landslide monitoring system, there will be multiple sensor nodes for covering whole downslope area, but for the sake of design simplicity, we will simulate only 7 sensor nodes using Wio-E5 Dev Kit and Arduino Mega 2560, which includes 2 soil moisture sensors, 1 MEMS accelerometer, tipping bucket rain gauge sensor, vibration sensor, temperature and humidity sensor. As shown in this figure, all these LoRa sensor nodes will be then connected to gateway node. At gateway node, we will use another LoRa development board by Seed Studio, that is Wio-E5 Mini, interfaced with ESP8266. As figure shows, the gateway node will be at some distance from other wireless sensor nodes at landslide prone area. This gateway node also includes some sensor, like another tipping bucket, rain gauge sensor and temperature humidity sensor. This is just for conveying rain density difference in landslide prone areas and other surrounding areas. Gateway device will receive WSN data from different sensor nodes from landslide prone area. Then, it will add data from its own area. Then finally combining both places data together in one frame, it will send it to the end nodes. We will use Wio terminal interfaced with Groove Wio-E5 module as an end device. It will receive data relayed by gateway device. Now once we receive all the sensor data from the landslide prone places, at well-connected cities, we can do anything with it, like cloud sharing, processing, analysis, prediction and early detection. So, by monitoring descending velocity of mass in landslides, or subsidence over period of time, and by using statistical analytical techniques of likelihood findings, we can predict or early detect the landslide events, and eventually concerned authorities can take evacuation and safety measures as per the findings. Okay, so this is the functional block diagram for each node including components. Sensor node consists of 7 different sensors. Those are rain sensor, vibration sensor, 2 soil moisture sensors, DHT22 temperature and humidity sensor, and a DXL345 accelerometer. Arduino Mega 2560 is interfaced with all these sensors, and TFT display is used to display the sensor readings locally. To transfer all these sensor data to the end node, over LoRa, Wio-E5 LoRa dev kit is also connected to Arduino. For gateway node, we have used Wio-E5 mini LoRa board, interfaced with Node MCU ESP8266. Here also there are 2 sensing elements connected, rain gauge and DHT22 sensor. OLED display is used to display the sensor readings, LoRa signal strength and status of sensor node. Gateway node receives data coming from sensor node and relay it to end node via LoRa. At the end node, we have used Wio terminal interfaced with Wio-E5 LoRa module to receive the data coming from gateway node. So you can see that, with this method of point-to-point LoRa, we can make custom gateway node to relay data up to 10 to 20 kilometers from landslide-prone sites. So this was all about functional block diagram of the project. Now let's look into actual circuit diagrams and schematics in detail, and let's see how all these components have been connected together. Alright, so this is a circuit diagram of sensor node. You can see DHT22 sensor, vibration sensor, 2 soil moisture sensors, 1 resistive and other is capacitive, a DXL345 accelerometer, 1.8-inch TFT display. All connected to Arduino Mega 2560. Wio-E5 LoRa development kit works at 3.3 volts logic level. So this logic level shifter module is used to bring down Arduino's 5 volts logic to 3.3 volts, compatible with this Wio-E5 kit. This is the MB102 breadboard power converter module. This module converts 9-volt battery or USB power supply to 2 power rails, 5 volts and 3.3 volts. Wio-E5 requires more current, so it should be powered from external power supply rather than Arduino's. If you do so, make sure to connect all ground connections to common. A tipping bucket rain gauge is quite expensive investment for this project, hence we decided to simulate it using simple potentiometer of value 10 kiloohm. This resistive soil moisture sensor, this potentiometer, and this capacitive soil moisture sensor have analog outputs, therefore, they all connected to A0, A1 and A2 analog pins of Arduino Mega, respectively. This is 1.8-inch TFT display. It uses SPI interface. All the pin connections are given in this table. You can refer it for more details. This is a DXL345 MEMS accelerometer, connected with I2C interface. Its I2C lines SDA and SCL have been pulled up to VCC via these two pull-up resistors of 4.7 kilo-ohm. These two sensors, DHT22 and vibration sensors, gives digital outputs, hence they are connected to digital inputs of Arduino. This is Wio-E5 LoRa development kit. Its TX and RX lines are connected to Mega's RX1 and TX1 lines, respectively, via this level shifter module. So you can see, all wiring connections are in color coding, hence you can easily track them. You will get this schematic on our GitHub page. Please note that this image is of high resolution, so you can zoom in further to track any connection and follow along to replicate it on your breadboard. Alright, now let's move forward and see next circuit diagram, which is of the gateway node. In gateway node, ESP8266 is connected to this 1.3-inch IPS display with I2C interface. All display pin connections are given in this table. This potentiometer posing is tipping bucket train sensor. It is connected to ADC0, that is A0 pin. This is Wio-E5 Mini LoRa dev board. This has been powered with 5 volts from V-in pin of ESP. As both ESP8266 and Wio-E5 Mini works on 3.3 volts logic level, so here we won't need any level shifter module. DHT22 temperature and humidity sensor is connected to D6 digital pin. This is all about gateway node connections. Now let's see the schematics of end node. End node is pretty simple in connection, just plug and play. Here is the Wio terminal dev board, which is connected with this Wio-E5 LoRa Groove module. It has same chip, STM32E5 LoRa, as of other two LoRa dev boards. We will also share the other circuit diagrams for each individual interfacing of components. We highly recommend you to go stepwise, test all devices with separate interfacings, and then combine them all to make final project. We will share all circuit schematics on our GitHub page. Links will be shared in the description of this video. Okay, now let's move forward and see programming of the project. Source codes explanations. For that, let's move over to the Visual Studio Code. First we will see the code for sensor node. Here is the one. As you can see, all code is well commented and easily understandable by just overlooking. Let me show you. Here initially, we have included all the necessary libraries required, like graphics, display specific, DHT sensor, and ADXL345. Which also can be verified and seen here in Platform IO project configuration file. We have added detailed comments for each section of the program to easily understand for what purpose that code snippet is used there. Therefore, you can understand what's going on with these functions and variables. So, similarly, for other two interfacing circuits, which are the gateway node and end node, in their respective code implementations, we have added detailed comments to each important code snippet, functions and subroutines, to guide you through these code implementations. Besides, if you have any doubts, questions or suggestions, or found any bugs in code, please feel free to contact us on WhatsApp or Telegram. All these source code will be available on project's GitHub repository on our GitHub page. We will share all the links in description. Okay, now let's see the actual project demo. So here you can see, we have arranged all 3 node circuits on the desk. So, you can see, this is our WSN node. This is the gateway node, and this is an end node. Let's see each one by one. So, this one is our wireless sensor node which uses LoRa technology. We have assembled it as per circuit diagram which we have discussed earlier. This is an Arduino Mega 2560. This is 1.8-inch TFT display. This is level shifter module. Wio-E5 dev kit. Vibration sensor. Resistive soil moisture sensor. Capacitive soil moisture sensor. This is MB102 breadboard power converter module. We have used this 7.4 volts LiPo battery to provide power to it, which then convert two power rails, 5 volts and 3.3 volts for other circuitry. This is potentiometer working as tipping bucket rain gauge. DHT22 sensor. A DXL345 accelerometer mounted on this small breadboard. Then here is the LoRa gateway node circuitry. Consist of node MCU ESP8266 as mainboard. Interfaced with Wio-E5 Mini. 240 pixel IPS OLED display. DHT22 sensor. And this pot is posing, as we said earlier, the tipping bucket rain gauge sensor. And this third circuit assembly is the LoRa N node, consist of Wio terminal and Groove Wio-E5 module. So this was all about circuits and their assembly. Now let's test this assembly and find out how it works. We will surely try our best to field test it afterwards, as per time permits, but for the time being, let's first check it's working here in lab. Please note that this is just simple DIY prototype for testing application of LoRa WSN in landslide monitoring systems. In actual real-time landslide monitoring systems may have completely different setup, different sensors, advanced controllers, and other high-quality components, which would have way better resolutions, performance and response time than our prototype. Our DIY project is purely for academic and study purpose. It is not optimized, designed, or intended for deployment in actual landslide hazard-prone sites or likelihood areas.
I just wish he knew.
We will first turn on the circuit of end node by powering Wio terminal through this USB cable. On display screen there will be no readings, since it is not yet receiving anything from remote sensor node or from gateway node. Now, let's turn on the gateway node circuit by powering node MCU via USB cable from power bank. After initial processing, display will show local temperature, humidity and rain sensor readings. SN status. This SNR and RSSI will get displayed whenever it receives any LoRa packets from sensor node.
I just wish he knew.
Finally, let's power on the WSN sensor node circuit. Arduino Mega will fetch all sensors data, then display it on TFT display. And then send it to gateway node through LoRa, using this Wio-E5 dev kit. In this way, you can see, we can successfully send data from the sensor node to gateway node, which is showing LoRa packet signal stats. On other hand, at the end node, it also got data relayed by the gateway node. So, this was just a lab test. We have tested lab trial by using Seed Studio's Wio-E5 series LoRa development boards. We can transmit data from one remote landslide area where there is no wireless connectivity of cellular and Wi-Fi to the end node, which can be in range of 10 to 15 kilometers, which needs to be confirmed by actual field testing. We will try to do that in upcoming videos. Okay, so, in this way, we have seen detailed review and DIY project using these amazing LoRa development boards, Wio-E5 Mini and Wio-E5 LoRa Dev Kit, manufactured by the Seed Studio. In previous part, we have seen its unboxing, features, specifications, datasheets, AT commands configuration guide, and we have also seen demo of serial configuration of these boards via AT commands. In the next part, we will test this DIY project prototype in open area in real time. We will check its transmission range. Stay tuned for more updates. Meanwhile, if you want to purchase these LoRa boards, you can directly go to Seed Studio's website. Links are shared in the video description. Alright, stay tuned for more projects and tech updates. If you face any difficulty in replicating any of our DIY project, feel free to ping us on Telegram or WhatsApp. You can also send us email at support@make2explore.com. We would be happy to help. Thank you.